In this video, we're going to go over the reaction between an alcohol and a carboxylic acid. So what do you think is the major product of this reaction? Well, let's begin. Whenever you mix an alcohol and a carboxylic acid, it's going to be a dehydration reaction. Water is going to be removed, and you can simply condense or bring together the two remaining parts. So we're going to get an ester anytime you mix an alcohol with a carboxylic acid. And here's the H2O side product. Now this reaction is reversible, and you need an acid catalyst to speed it up. Otherwise, it's going to be very, very slow. So in the next example, to draw the reaction, or the product of the reaction, all you got to do is remove H2O and connect the remaining two groups together. So we're going to get a different type of ester. This is called an esterification reaction. There we go. I destroyed that word. Okay, so now let's do the same for the other product. Simply remove H2O and connect the two groups together. So that's how you can quickly determine what the major product is of an esterification reaction. All you got to do is draw the alcohols facing each other and simply remove water. But now, let's go over the mechanism for this process. Actually, before we do that, feel free to try these examples, because sometimes you can have two alcohols in the same molecule, or not two alcohols, an alcohol and a carboxylic acid. That's what I meant to say. So, in the presence of an acid catalyst, what do you think the major product for the first one will be? You need to know that this oxygen will eventually connect to this carbon, and basically we need to remove water. We're going to take away this OH and this H and connect this oxygen with that carbon. So let's count it. 1, 2, 3, 4, 5, 6. We know we're going to get an ester. We know that whenever we mix an alcohol with a carboxylic acid, it's going to give us an ester. But when those same two functional groups are found within a single molecule, you're going to get a cyclic ester whenever you have an intramolecular reaction. And there's going to be 6 atoms in this ring, including the oxygen atom. So that's how it looks like. Now in the next example, we know this alcohol is going to combine with this carbon. And if we count it, let's say this is number 1, 2, 3, 4, 5, 6. So we have another 6-membered ring. However, we have a few substituents on that ring. So this is carbon 1, this is 2, 3, 4, 5, and the oxygen is number 6. So on number 2 we have a methyl group, and on number 3 we have a dimethyl group. So that's the product of the intramolecular reaction between an alcohol and a carboxylic acid. But now let's go over the mechanism for this reaction. Actually, feel free to try it first. Propose a mechanism for the production of ethyl acetate. Let's use phosphoric acid as our acid catalyst. How would you do it? Well, the first thing that happens is the carboxylic acid is going to be protonated by the phosphoric acid. And here's how you draw phosphoric acid. It looks just like that. So this oxygen is going to grab a hydrogen, and this oxygen-hydrogen bond is going to break. So now that we have a protonated carboxylic acid, it's activated towards nucleophilic substitution reactions. So then the alcohol molecule is now attracted to this partially positive carbon atom, and when it attacks it, this pi bond will break, giving us this tetrahedral intermediate, which looks like this. So this oxygen still has a hydrogen. It came from ethanol, and we need to get rid of it. Now our goal is to transfer a hydrogen from here to here, and we're going to do that using a solvent. You see, right now an OH is a bad leaving group, but we need to get rid of that OH to make the ester, so we got to turn it into a good leaving group. So we're going to use another ethanol molecule to get that job done, since there's plenty of ethanol molecules in the reaction chamber. So ethanol is going to grab this hydrogen, and this pi bond, or that single bond, is going to break. Not a pi bond, but a sigma bond. So this is what we now have. So now we have a protonated ethanol molecule, and it's going to transfer the hydrogen to the hydroxyl group. So hydroxyl is going to grab this hydrogen, and those electrons will return back to the oxygen atom. So what we now have is a protonated OH group, which will soon leave as H2O. So now this oxygen is going to form a double bond and expel the water molecule. So now we have a protonated ester. Now the water molecule that we've used, that came out, we can use that to grab the hydrogen, or we can use another ethanol molecule too. It's the same. And so now we have ethyl acetate and H3O+. We still have the H2PO4- in a solution somewhere. So if these two react, we can regenerate the H3PO4 catalyst that we had at the beginning. But now, let's work on some retrosynthesis problems. So let's say if you're given this ester, what alcohol and carboxylic acid was used to create that ester? How would you figure it out? And feel free to pause the video and try that example. So while you're working on that, I'm going to write up a few more problems. So go ahead and find the alcohol and the ester and the carboxylic acid that combine to form that particular ester. And try this one too. Okay, so let's start with the first example. Now, what we need to do is we need to cleave this bond, because that's the new bond that was formed to combine the alcohol and the carboxylic acid. So once we separate it, draw what you see on the left side, which looks like this, and simply add a hydrogen to that oxygen. In a reverse reaction, we need to add water. Now, draw what you see on the right side, and then simply add a carboxylic acid to the carbonyl group. And that's how you can get the alcohol and the carboxylic acid that join together to form that product. So now let's look at our next example. Let's break the carbon-oxygen bond. So on the left side, we can see that we needed phenol for that reaction. And on the right side, all we need to do is add an OH group to the carbonyl carbon. And so those are the two molecules that were needed to make this particular ester. and that's called, I believe, phenylacetate. Now what about this cyclic ester? How can we make it? Now if you have a cyclic ester, the alcohol and the carboxylic acid functional groups are in the same molecule. So if you have a straight chain ester like this, the carboxylic acid and the alcohol that makes that ester are like on separate molecules. But here, they're on the same molecule. So what we're going to do is first, we're going to cleave that bond. So here's what we have. And then we're going to add an OH to both of those groups. So that's the molecule that we need to make that particular ester. And that's it for the reactions between carboxylic acids and alcohols. There's many ways you can make different esters, but this is just one of the common ways of doing it. So thanks for watching this video.